In this video, we will discuss center of mass, an important concept closely related to the last chapter, momentum, and the next chapter, rotation. The first thing to say about center of mass is that the center of mass is not an object. The center of mass is a location, a point. Colloquially, when we think of center of mass, we think of something like a balance point, a location where we can support an object without it tipping over. If an object is uniform, we think of the center of mass as being somewhere in the middle. If it is heavier on one end, the center of mass shifts in the direction of the heavier end. So, center of mass depends on the distribution of mass in space. We could define the center of mass as the location for an object where the distributions of mass on all sides are balanced. There are three main reasons why the center of mass is an important quantity. First, in every puzzle we've seen in this course so far, we have always ignored any internal motion of an object. When we considered a skier traveling downhill, we didn't account for their repeated reorientations of their legs, let alone the subtle counterbalancing of their arms or head. We treated them as a single, rigid, point-like object. In reality, we have always been focusing on the motion of their center of mass. Consider this object being thrown through the air. The motion of the object is quite complex. But if we were to follow just the center of mass, shown here in orange paint under a black light, we would see it moves in the familiar parabola of projectile motion. This is the first important point about the center of mass. Every object behaves as if all its mass were concentrated at one point, the center of mass. As long as we're not examining the rotation of an object, we are allowed to represent any object as a single point with the original mass. But now, since I've brought up rotation, how is that affected by the center of mass? Look at this disk as it is thrown. It is rotating around its center of mass. This is characteristic of rotational motion for any object as long as it is not attached to hinges. This plunger rotates around its center of mass, and this asteroid likewise. This is the second important aspect of center of mass. If an object is not on hinges, it always rotates around its center of mass. Let's explore that point a little more closely. If I throw this hula hoop into the air, we see it rotating about its center. That makes sense because that's where the center of mass is. But notice something weird. The center of mass is not contained within the actual material of the hoop. This is something we have to be careful about. The center of mass does not need to be within the physical body of an object. Depending on the shape, it can lie outside the physical body of an object. The third important point about center of mass is visible when we see collisions. Here is a familiar elastic collision between two balls of equal mass. It's easy to calculate the center of mass of the two balls. We will mark it with a cross. Initially, one ball is moving. The center of mass has to move with it, and the masses get closer together. After the collision occurs, each ball moves in its own direction. But if we recalculate the location of the center of mass, we see it keeps moving in a straight line. This is another important characteristic closely tied to momentum. When any collision occurs, elastic or inelastic, the center of mass always moves in a straight line. So now that we know what it is and why it's important, let's see the equation. It turns out there are two different equations for center of mass. The first one applies when we have collections of discrete objects, like a set of asteroids. We multiply the mass of each by the position of each, then add up those products, and then divide by the total mass. If we're dealing instead with a continuous body, like a rod or a disk, we use this equation, which uses integrals. Now, an integral basically cuts an object into many little slices and then adds all those slices together. That first symbol is the Greek letter rho, and it represents the density of the slice, that is, the mass of the slice divided by its volume. In the top integral, we take the density of the slice, rho, multiply by its position, x, and then multiply that by the cross-section area, a. The integral then adds up all those products for all slices. The bottom integral is similar, but doesn't include the position, x. Then we divide the two integrals. Let's explore these equations in several puzzles. The simplest puzzles involve discrete objects in one dimension. Here, a 3 kilogram object is located at the origin. A 1 kilogram object is located at 4, 0. A 2 kilogram object is located at 7, 0. Where is the center of mass of the system? In this question, we have a Cartesian plane and, more importantly, an x-axis, kind of like this. We have a 3 kilogram object which is located at the origin. We have a 1 kilogram object that is located at 4 I hat. And we have a 2 kilogram object that is located at 7 I hat. And what we want to find is the center of mass. Piece of cake. The equation for center of mass is the location of the center of mass, which is symbolized by x sub cm, is equal to the sum of the masses times the x positions of those masses. So for each one of these masses, we multiply its mass multiplied by its x position, divided by the sum of the masses. So what does that work out to? Let's go through these one by one. The first mass has a mass of 3, and its position is 0 I hat. Plus, the 1 kilogram object has a mass of obviously 1 kilogram, and it's located at 4 I hat. Plus, the 2 kilogram object, which is located at 7 I hat. All divided by the sum of all of these masses. So that would be 3 plus 1 plus 2. Let's simplify. 3 times 0 is 0, plus 1 times 4 is 4 I hat, plus 2 times 7 is 14 I hat, all divided by 3 plus 1 plus 2 is 6. So that's going to work out to 18 I hat divided by 6, which is equal to 3 I hat. So that is the location of the center of mass. It is located at 3 units along the x-axis. Now, as I mentioned before, notice that there is no actual object located at 3 units. What matters, however, is that this is the location of the weighted average. This represents a position where the distribution of masses on the left of that position is exactly balanced by the distribution of masses on the right of that position. It's easy to expand this to 2 dimensions. Consider this question. A 3 kilogram asteroid is located at 0, 4. A 1 kilogram asteroid is located at 2, 0. A 2 kilogram asteroid is located at 3, 2. Where is the center of mass of the system? Let's start this question by drawing our axes. We were told that there were 3 asteroids, but this time they are located in 2 dimensions. So I'm going to draw my axes as follows. There is a 3 kilogram asteroid which is located at the position 0, 4. There is a 1 kilogram asteroid that is located at 2, 0. And there is a 2 kilogram asteroid that is located at 3, 2. And we can fill in the rest of the coordinates if we so desire. So for the sake of clarity, I will put these in. Now we want to find the center of mass of these 3 asteroids. Let's go ahead and do that. In the x direction, the x location of the center of mass is given by the sum of each mass multiplied by its x position divided by the sum of the masses. So that would work out to the 3 kilogram asteroid is located at an x coordinate of 0. The 1 kilogram object is located at 2 I hat. The 3 kilogram object, the 2 kilogram object is located at 3 I hat. All of that gets divided by 3 plus 1 plus 2. So 1 times 2 plus 2 times 3, that works out to 8 I hat divided by 6, which is equal to 4 over 3 I hat, or about 1.33 I hat. Now that only takes care of the x coordinate of the center of mass. Remember, the center of mass is a location, it's a point, but in 2-dimensional space, I need a y coordinate as well. Easy enough to find, we use the corresponding formula for y. The center of mass is equal to mass times the y coordinate divided by the sum of the y coordinates, which equals 3 kilograms located at 4 j hat plus 1 kilogram located at 0 j hat plus 2 kilograms located at 2 j hat. All this gets divided by 3 plus 1 plus 2. Again, the sum of the masses, but that doesn't change between x and y. So that works out to 12 plus 0 plus 4 is 16 j hat divided by 3 plus 1 plus 2 is 6. And that's going to work out to 8 divided by 3, which is 2.66 j hat, or 2.67 if you want to round it appropriately. So this location of the center of mass is 4/3 I hat, which would be 1.33 I hat, plus 2.66 j hat, which would be located at, here's 1.33, and 2.66 would be about here. So this is the location of the center of mass of this system of 3 asteroids. For a continuous object, we will visualize taking a slice of the object and examining its density, position, and cross-section area. Consider this question. A rod is 0.5 meters long and has a cross-section area of 0.01 meters squared. Its density is 6 kilograms per meter cubed. Where is its center of mass? Here is a picture of what this block would look like. Something like that. Now, I'm going to draw the axis for this something like this. I'm going to set the x-axis to ride midway through this block. So we can imagine this emerging from the exact center of this face of the block. We don't really need to bother with the y direction. Now, because we are dealing with a continuous object here, we're going to need to use some calculus in order to solve for where the center of mass of this block is. The exact equation looks like this. We need to take the integral of the density multiplied by the position along this block, multiplied by the cross-section area of the block, dx, over integral of density times cross-section area times dx. So very similar top and bottom, but what the top has an x and the bottom one does not. So let's write down all of the information that we know. We know that the density of this block is 0.6 kilograms per meters cubed. The length of this block is 0.5 meters. The cross-section area of this block, which I'm going to shade where that is, that would be this face over here, that would be an example of the cross-section area, is uniformly 0.01 meters squared. So no matter which part of the block I start talking about, it's always going to have the same cross-section area. And we're going to examine that a little bit more closely when we go about actually splitting the block into slices so that we can take the integral. So let's take some random slice of this block. Let's take this one. Now, for this slice over here, the thickness of this slice is dx, and the cross-section area of this slice, which I'm going to shade over here, is the same as the cross-section area of the overall block. So I could say that the cross-section area here and the cross-section area here are the same. So now we have all of the information that we need in order to solve for this integral. All of this is equal to the x location of the center of mass. So this is going to be the integral over the entire length, so that's 0 to 0.5, times the density, which I said was actually 6, not 0.6, times x, which is the location of this particular slice, but since I picked a slice at random, that means I just need to leave it as x, times the area, which is 0.01, dx, divided by the integral of 0 to 0.5 of 6, because 6 is now the density, multiplied by the area, 0.01 dx. Okay, 6 times 0.01 will give us 0.06, but 0.06 is a constant, and whenever something is multiplied by a constant inside an integral, it can be taken out of the integral. So I can simplify this whole thing and write it like this. 0.06 integral from 0 to 0.5 of x dx divided by 0.06 integral 0 to 0.5 of dx with nothing inside. The 0.06 and the 0.06 on the bottom are going to cancel each other out. So that's just going to leave me with these two integrals. The integral of x is 1/2 x squared, running from 0 to 0.5. And the integral of dx is x, running from 0 to 0.5. So this whole thing is going to work out to half of 0.5 squared minus half of 0 squared, all divided by 0.5 minus 0. When we write it in this notation, you have to plug in the upper limit in for x, then plug in the lower limit for x, and then subtract the lower limit from the upper limit. So what I've done is I've copied over this function twice, but the first time I've plugged in the upper limit, the second time I've plugged in the lower limit, and then I've subtracted. So half times 0.5 squared will work out to 1/8, which is 0.125. 0.5 minus 0 is 0.5. So 0.125 divided by 0.5 is going to give us 0.25. And this is in x, so we have to tack an I hat on the end. So what this means is that for a block which is 0.5 meters long, the center of mass is located at 0.25, about halfway down, in fact exactly halfway down the middle of this block. This is where the center of mass is located. And just to make it a little bit clearer, I'm going to run over it in marker as well. So exactly halfway down the middle of the block is the center of mass. The picture gets a little more complicated when the cross-section area varies from slice to slice. Consider this question. A triangular plate has corners located at 0, 0, 1.2, and 1, -0.2. Its thickness is 0.01 meters. Its density is 2 kilograms per meter cubed. Where is its center of mass? In this case, we have an object which is basically two-dimensional. It does have some thickness, but that thickness isn't changing. And when thicknesses aren't changing, or any factor isn't changing, it's usually pretty easy to deal with or even to cancel it out in a question like this. This object has a shape which is triangular, like that. The base of the triangle is located at x equals 1. This point of the triangle, this corner of the triangle, is located at y is equal to 0.2, and this corner of the triangle is located at y equals -0.2. The triangle has a body which gives it a certain amount of thickness. I'm going to shade that in over here. Okay. And we are being asked to find where the center of mass of this triangle is. Before we start doing that, what I would like to do is I would like to find the equation of this line over here. And the reason why we're going to do that is we're going to approach the center of mass in exactly the same way we did it before. We're going to take a slice of this object, something like this, and because this is an object that has some thickness, the full slice is going to look something like a rectangular prism. Like that. Now, for this slice, the thickness is going to be the same as the thickness of the overall arrow, or this triangular shape. The width of this slice is going to be dx, because that's what the width of the slice always is, but the height of the slice is not that easy to find out. Because the height is changing. If I were to take a slice closer to the tip, it would have one height, but if I took it closer to the base, I would have a different height. So what we have to do is we have to find an equation for that height with respect to where the slice is taken along this x-axis. Let's write down all of the information that we know. We know that the thickness of this arrow-shaped object is 0.01 meters. The density is 2 kilograms per meter cubed. And that's the large stuff that we have been told. Now, I mentioned earlier that I wanted to find out what was the equation of this line, and now we can appreciate why that's going to be necessary. It's because the height of this is going to be given by what is the equation of this line, which defines what the boundary of this slice is going to be. So we need to find this line over here. Now, for this line, we can see that it passes through the origin, so it contains the point 0, 0, and it also is going to pass through the location 1 meter out, and the point 0.2, because that's the position of the corner of this. We need to find an equation for a line, a straight line that passes through these 2 points. Easy enough to do. The slope of such a line would be given by y2 minus y1 divided by x2 minus x1, which is going to be y2 minus y1 is 0.2 minus 0 divided by x2 minus x1 is 1 minus 0, all of which works out to 0.2. And because this is passing through the origin, there is no y-intercept, or rather the y-intercept is equal to 0. So we have y is simply equal to 0.2 times x. That is the equation of this line. That is also the equation of the of this side of the triangle. And we're going to use that to find out what the length of this strip is. Because if this line has an equation of 0.2x, that means that the distance from this line to the x-axis would be 0.2x. But there's a line on the other side as well, right? And it's in fact a mirror image of that. So the distance from the x-axis to this bottom line is given by the same thing, 0.2x. So the length of this strip is now 0.2x plus 0.2x, which is equal to 0.4x. That gives us all of the information we need. We now have the length of this strip, which is 0.2x doubled, or to 0.4x, the width of this strip, which is always dx, and the thickness of this strip, which is the thickness of this plate, which is 0.01 meters. That gives us all the information we need in order to set up the center of mass equation. So, the location of the center of mass is given by integral of density times x times the cross-section area dx divided by the integral of density times the cross-section area times dx. Let's plug in everything we know. The integral is going to be taken from 0 to x equals 1. That will apply to both integrals. The density of both of them is 2. There's an x in the top integral, it's not there in the bottom integral. And the cross-section area, the area of this face, which I have shaded in our strip, is going to be the length multiplied by the thickness. So the length was given by this total 0.4x multiplied by the thickness, which is 0.01. These two multiplied together give us the cross-section area. Dx in the top, dx in the bottom. Now, let's start simplifying all of this. The integral from 0 to 1 of 2 times 0.4 gives us 0.8. 0.8 multiplied by 0.01 gives us 0.008. And x multiplied by x will of course give us x squared. Divided by the integral from 0 to 1 of 2 times 0.4 times 0.01 gives us 0.008 x dx. 0.008 and 0.008 can come out of the integral because these are constants, and whenever you multiply by a constant, those constants can always come out. So that gives us 0.008 times the integral from 0 to 1 of x squared dx divided by 0.008 integral from 0 to 1 of x dx. The 0.008 and the 0.008 cancel out. And when we evaluate this, this is going to give us the integral of x squared is 1/3 x cubed. That gets evaluated from 0 to 1. Divided by the integral of x is going to be 1/2 x squared. Also running from 0 to 1. Let's plug in these bounds and let's solve for what this whole thing works out to. 1/3 of the upper bound is 1 cubed minus 1/3 0 cubed divided by 1/2 of 1 squared minus 1/2 of 0 squared. So 1/3 of 0 cubed and 0 squared obviously go down to 0. 1/3 of 1 cubed is just going to be 1/3 divided by 1/2 of 1 squared also gives us 1/2. So it comes down to 1/3 divided by 1/2. When we simplify all that out, that gives us 2/3. 2/3 I hat. That is the location of the center of mass of this arrowhead over here. If the arrowhead has a length of 1 meter, then the center of mass is about here. 2/3 of the way down from the apex to the base. Right about here is the center of mass of this arrow. The same technique can be applied to still more complex shapes, like a cone. Consider this example. A cone is 0.6 meters tall and has a base radius of 0.2 meters. Its density is 9 kilograms per meter cubed. Where is its center of mass? We'll start this question by drawing our usual axes and drawing the cone as follows. So this is supposed to be symmetrical, but at this point you should be used to my lack of drawing ability. The radius of this base is 0.2, and the height of the cone is 0.6 meters. Now, we are going to take a slice of this cone like this. So a slice of this cone would look a little bit like a coin. Each slice would have a surface area, which is given by this area that I've just shaded. The thickness of the slice is, as usual, dx. The area, however, is going to change. At the tip, the area of this coin is going to be 0 because we're taking the cross-section of a point, but it'll grow to its full size at 0.6 meters. So we need to be cognizant of that. We're going to need to figure out how to express that. What other information were we given? We were told that the density of this cone is 9 kilograms per cubic meter. Now, let's see if we can figure out a relationship between the area of this slice, or the area of this cross-section, and its location along the x-axis. Well, let's think about what we know. This cross-section is a circle. The area is given by pi r squared. So we need to find the radius as a function of the location. We know that when x equals 0, the radius is also going to be 0. So that means that 0, 0 must be one relationship between the x location and the radius. We also know that when x equals 0.6, the radius is the full 0.2. So 0.6, 0.2 must be another relationship between the location and the radius. Now, we can express this relationship linearly. We can say that the radius is going to be equal to, first let's figure out what the slope would be. Because this is a linear relationship, so we can find out the slope quite easily. The slope is equal to the radius, which is 0.2, radius of the second coordinate minus radius of the first coordinate, divided by x for the second coordinate minus x of the first coordinate, which works out to 1/3. So the radius is always equal to 1/3 x, and since both of them become 0 at the origin, there's no y-intercept to add to this linear equation. This is the relationship between the location and the radius. We're now ready to solve for the center of mass. Here's how we do it. Again, we start with our equation, rho times x times the area dx divided by rho times the area of x dx. Again, very similar, but there's an x in the top, but there isn't in the bottom. Plug in everything that we know. The integral going from 0 to 0.6, rho is 9, x is just the location of this slice, which is x. The area is given by pi times the radius squared, but the radius itself is equal to 1/3 x, and that's the thing that gets squared. And finally, we have a dx to cap it all off. The bottom is going to be integral of 0 to 0.6 of the density, which is 9, multiplied by the area, which is pi times 1/3 x squared dx, exactly the same as what it was up here. Now, let us start simplifying all of this. 1/3 x squared is going to give us 1/9 x squared. So this is going to work out to 9 times x, or integral from 0 to 0.6 of 9 times x times pi times, again, this squared is 1/9 of x squared dx, divided by 0 to 0.6 of 9 times, again, we do the same operation, pi times 1/9 of x squared dx. Now, let's look at all of these constants that we have here. We have a 9, we have a pi, and we have a 1/9, all of which are multiplied together. So we can multiply all of these and we can pull them all out. The 9 and the 1/9 will cancel and we'll just be left with pi. So that's going to give us pi times the integral of 0 to 0.6 of x times x squared is x cubed dx, divided by 9 times pi times 1/9, again gives us pi, and that's the number that we pull to the outside, 0 to 0.6 x squared dx. Pi and pi will cancel, and the integral of x cubed is going to be 1/4 x to the 4th power, which has to run from 0 to 0.6 over x squared becomes 1/3 x cubed, running from 0 to 0.6. Now let's plug in everything and let's see what happens. We get 1/4 0.6 to the 4th power minus 1/4 0 to the 4th power, divided by 1/3 0.6 to the 3rd power minus 1/3 0 to the 3rd power. 0 to the 4th power, 0 to the 3rd power, obviously these are going to be 0, both of them. So we just need to find out what is 0.6 to the 4th power and what is 0.6 to the 3rd power. For this, we need our calculators. 0.6 raised to the 4th power is 0.1296. And a quarter of that is 0.0324. Divided by 0.6 to the 3rd power is 0.216, and that divided by 3 for 1/3 is 0.072. So the last step is to just divide 0.0324 by 0.072. 0.0324 divided by 0.072 gives us 0.45. So 0.45 I hat meters. That is, since 0.45 is 3/4 of 0.6, that means that the location of the center of mass must be pretty close to the base. It's 3/4 of the way down from the tip to the base, so somewhere about here. It's further down than what it was in the arrow, and of course much further down than what it was for the rectangular prism that we saw earlier. This is the location of the center of mass. In this video, we explored the concept of center of mass and saw how to solve it for discrete and continuous objects. In the next video, we will begin the unit of rotation, starting with rotational kinematics.